Now, here's a question, which is the kind of question that I'd like to ask on a test because it forces you to create something and then use a technique we've seen in class to solve it. So we're asked to create a linear system with two unknowns and three equations, such that 1 is its unique solution, and then we're asked to solve it using Gaussian elimination. So we have two unknowns, so we need to create this system, right? We can think about the fact that we're in R2, right? There's X and Y, those are my unknowns, and 1 is going to be the solution. So what I'd like to create essentially are two lines that intersect at 1. So how can I do that? Well, for instance, I could start with some random line like this, okay? 2x minus y equals to what? Well, I want 1 to be part of that line. So which means that if I replace x by 1 and y by 1, it has to be a solution. So if I do 2 times 1 minus 1, I actually get 1. So now I'm guaranteed that this line goes through 1. After that, I'm going to create another line, but I want to choose one that's non-parallel to this one because I don't want to have infinitely many solutions. So maybe x plus y equals to what? Well, once again, I'd like 1 to be part of that line. So this way both lines will intersect at 1. So 1 plus 1 is 2. So right now I've got two lines that clearly intersect at 2. If you're wondering what those lines look like, well, I just drew them in the Cartesian plane. Now, I want a third equation. So what I could do is essentially, there are two things I could do. I could just take one equation and multiply it throughout by a constant to get something that's slightly different, but still the same equation as one of the two above. So this is what I actually decided to do. So I took the second one and I multiplied it throughout by 3. Okay, and then I'm creating an equation. It looks kind of different, but it's actually the exact same equation as number 2. So that would mean that I would still have this unique intersection point 1 because that third equation describes a line that just overlaps the line with equation x plus y equals 2. Actually, this is a 2 here. Something else you could do is that would seem to create something that's way different is to take, I don't know, equation 1 and 2, you could add them up. Okay, adding them up, you'd create this equation, 3x equals 3, something like that. Or that looks super simple. So maybe we could subtract them. If I subtract them, I get this. So it looks different, but actually it's redundant. So it's still would give me a line that would cross at 1. So you could also add a line, you know, like that. That's probably what this line is like. Something that still intersects at 1. So anyway, so I've chosen something simpler than that. I've chosen to just multiply throughout my my second equation. Okay, so I've got this system. Now I'm kind of sure that 1 is a unique solution, and I'm asked to solve this using Gaussian elimination. So by the way, one thing I want to show in this example is that this is redundant, right? It's not adding any extra information, because it's a copy essentially of equation 2. So once I will do Gaussian elimination, I should see that this equation could have been removed in the first place, which means that on the third row, I should see a row of all zeros eventually showing up. Okay, so let's do this. Okay, I start with my invented matrix. Now let's apply Gaussian elimination following exactly the recipe. So what I want to do is pick the leftmost non-zero column, which is this one, and put a leading one at the top. So I'm just going to divide by 2 the first row. So doing this, get 1 here, minus a half, 1/2, and I'm not changing the other lines. After that, what do? I want to put zeros here and there. So how do I do that? I take row 2 and I subtract a multiple of row 1. So in this case, I just need to subtract row 1. For row 3, I subtract 3 times row 1. And then what do I get? I get this. Here, I just copy the first row. And here I'm going to get 0, 3 half, 3 half, and 0, 9 half, 9 half. That's a 9 here. Okay, next step is I essentially cover up this row, move on and look at the remaining sum matrix, which is this. That's the remaining sum matrix here. And I reapply the algorithm. So I look at the leftmost non-zero column, which is this, and I'm going to put a 1 here. So to do this, I do 2/3 of row 2. So I just recopy row 1 and recopy row 3 like this. Then my next step is to put a 0 here. So how do I do that? I do row 3 minus 9 half row 2. So it's important to follow the recipe if you don't want to create important zeros that have been introduced already. So I don't want to destroy, you see those zeros here and there. I want to keep them. So if you don't follow the recipe correctly, you're going to destroy those zeros. So it's important to always work. You see here, this is the row with the leading 1 that I'm working with. Just like here, I was working with the row with the leading 1 in the first column. So okay, so if I do this, it's pretty easy to see. Oh, I get my row of zeros. Okay, so right there, I already know that this is redundant. Okay, so from this I get, from this row of zeros, we see that equation 3 is redundant. Now it looks obvious now because that's how I created my equations, but when you have like 10 equations, 10 unknowns, sometimes it's hard to see that one equation is actually redundant. But it will show up if you when you do Gaussian elimination. And then we have our matrix in row echelon form, so we can solve it using a backward substitution. So you have to understand, right, that right now I've got other equations, but that still have the same solution set as before. So that's how those equations read. Okay, so y is 1. So you do your backward substitution. So y is 1, you start with that. Okay, so y equals 1. And then after that, so I'm going to move up right like that. And after that, I solve for x. X is 1/2 plus 1/2 of y. And I'm going to replace y by 1. So that's 1/2 plus 1/2, which is 1. So therefore, 1, 1 is the unique solution. And that's it.